All right, so we're the Spectrum Analyzer group with group members being Marshall, myself, Sadie, Kevin, and Hui. Our technical advisor is Rick Hunter and project coordinator is Dr. Purdy. So first things first, what is the problem? So there already are many spectrum analyzers out there. The problem is that these spectrum analyzers would be pretty expensive for a university to allocate funds in their budget for. So what we are proposing is to have a spectrum analyzer of reasonable performance, something that a university would use to have their students debug circuits. They'll have a much more reasonable price point compared to this would be a middle of the road type spectrum analyzer offered by Agilent / Keysight. So that's what we're hoping to do, and let's get into, I guess, why do we do spectrum analysis to begin with? So I told you why we're wanting to build the spectrum analyzer, and that's because the current solutions are too high of a price for a university to afford. But why do spectrum analysis to begin with? And that's because time domain only tells you so much. So here's an example. Here's what looks to be, maybe this is an output of an amplifier, and you'd expect to see, a sinusoid. But, this is what looks to be a sum of sinusoids, and that's just an assumption. But there's really no way to prove that if you're just using time domain analysis. So that's where we turn to frequency domain analysis, or hook this output of your amplifier up to the input of a spectrum analyzer, and you'd see something like this. You'd see that, okay, note that this is DBC. So here's your fundamental frequency, and below that, 15 dB below that, you have your fourth, and 25 dB below your fundamental, you have your third harmonics. So that's where your problem lies. And without going to the frequency domain to debug the circuit, all you'd have would be assumptions on why it's not operating correctly. Here you're able to prove out your assumptions, and that's achieved by going to the frequency domain. So not only will a spectrum analyzer help students with debugging circuits, you're able to also do some important performance measurements, including bandwidth and phase noise measurements, if you're designing an oscillator or synthesizer or other clocking sources, something that I have done in my co-ops. So continuing, so I talked about why we do spectrum analysis. Let's get into how is spectrum analysis actually achieved. So there are two main architectures for spectrum analysis, one being a super heterodyne type and the other being a direct conversion type. So the main difference between these two architectures is the super heterodyne architecture has several frequency translation stages, where the direct conversion only has one conversion stage. For the super heterodyne case, obviously, as you have several frequency translation stages, you're going to have more parts. You're going to have a higher part count. But with this having multiple translation stages, you're able to relax the requirements on your ADC as well as your processor. So that's where you get some cost savings. Compared to the direct conversion stage, where you only have one frequency translation stage, though you need to have a very high sampling rate ADC and a powerful processor to process those samples. So that's where you run into the problem of, where we run into the problem for not adopting this architecture and going for the super heterodyne architecture, is due to the fact that this ADC can cost close to $2,000 just for the chip, and this processor can get pretty expensive too. So we're going to do this superhet architecture so we can save some costs there, as well as get some RF exposure, as it has as we'll be needing to design quite a few more RF components. So getting into why or what the objectives are for our product are and the constraints we have. So I touched on earlier some of the primary objectives we have are to have good performance, to be at a reasonable cost point, our product, and for the user to be able to use it. There's no reason to have a high performance spectrum analyzer spitting out this data and having, you're not able to interpret what the data means. So we got to be able to produce a GUI that illustrates this data that the spectrum analyzer, our hardware, is spitting out to the processor. And it's got to be able to present this data in a meaningful fashion such that you can make conclusions based on that data. Likewise, we got to have good performance. So a lab coordinator is going to want to purchase this spectrum analyzer as well. It's got to be of a reasonable cost point so that they can actually afford to put this into their budget. Likewise, a personal, or for our group, we gotta have this done by spring next year, and so we got to be very careful in hitting our deadlines. So how are we going to help alleviate some of these constraints of being under a certain cost, having reasonable performance, and getting it done in a certain time frame? Well, one way we're doing that is we're leveraging eBay for parts. So what we're doing is we're going to eBay looking for sellers that have already pre-made boards with parts placed on those boards from manufacturers such as Analog Devices and Texas Instruments that put out some high performance parts. So by doing that, we're not only saving costs because eBay is very competitive in their at what price they sell their items, but also we're getting reasonable performance as we're using parts from TI and ADI. Likewise, we're reducing our design-in time as we're not needing to lay out these boards. So it's a win-win-win.
Hello, my name is Sadie DeMuzio, and I will be going over some of the design process for our project. One of the design methods that we use is the function means tree, and our functions are shown as rectangles and our means are shown as trapezoids. So the main function of our project is to perform spectrum analysis, and some of the means for doing that include digital FFT, direct conversion, and heterodyne type spectrum analyzers. In our initial research, we found that the digital FFT and direct conversion spectrum analyzers were not really feasible as a senior design project as they required very costly components. So we instead decided to look at the heterodyne type spectrum analyzer. Our spectrum analyzer also has to perform other functions, including manipulating the signals for digital processing, storing and processing the data, as well as controlling the sweep. And the design process for all of these trees sort of follows the same steps. So we have a function that we want to perform. We identify multiple means for performing said function, and then eventually we choose one of those means and then continue down the tree, selecting, researching different functionality, and then selecting new means. And the dark blue is shown is the functions and means that we eventually chose. For our final design, we chose to construct a two-stage super heterodyne type spectrum analyzer. This design has several benefits. It's less expensive than the FFT and direct conversion type in its component cost. It also, the design we chose is a two-stage superheterodyne, which is going to take less design and time than a three-stage superheterodyne spectrum analyzer. So in this diagram, we have a basic heterodyne design. We have an input frequency and a local oscillator frequency and a mixer. And this configuration allows us to either up-convert the input frequency or down-convert the input frequency to a desired intermediate frequency. And the IF frequency typically depends on our later component specifications. In our design, we have two stages. We have the first stage is a up converter and the second stage is a down converter. So the up converter is chosen because we found that if you take this first frequency and to a very high frequency, it actually reduces the unwanted frequency signals caused by this first mixer. And the second mixer simply takes this higher frequency and converts it down to a level that can be easily handled by an inexpensive detector and ADC. Another benefit of this heterodyne analyzer is that it gives us RF hardware design experience, which is valuable to those of us who are pursuing careers in RF fields. This slide shows our desired specification for our final product. Our project is intended to be used as a lab equipment for students. The qualitative requirements reflect this. It must be powered through a standard wall outlet, able to fit on a lab bench with other equipment. It also must be durable for daily use, and especially by students who aren't familiar with spectrum analysis. It also requires a USB interface for control from either a lab computer or a student computer, and the software interface must be easy to control or reflect the something that the student may see in a workplace environment. And our quantitative requirements are our specifications for the actual spectrum analyzer, and they include the input frequency range, maximum input power, our analog frequency resolution, and our dynamic range. So on this slide we have our black box design of our final product, and so the student can connect a inputted signal such as a signal generator or an antenna to the spectrum analyzer, and the output is a graph plot of the frequency spectrum displayed on a monitor or their computer. And if we take the lid off of our box, we have our final design, which consists of three different kinds of components. It has RF analog, a digital component, and a software component. So just to go over this briefly, our analog components consist of everything from this low-pass filter all the way through to this driver. And our digital components include the MCU and the ADC. And our software component is going to be LabVIEW, which is installed on a computer, and that communicates to the MCU via USB. And we'll go into more detail on this design in our later slides.
Hi everyone, so my name is Hui Tran and I'm Electrical Engineering, class 2018. So today I'm gonna present the hardware design. So as you can see in this diagram of our spectrum analyzer, the spectrum analyzer has two stages. Each stage consists of a local oscillator, a mixer, some filters, and some amplifiers. So in the first stage, which is the upconversion stage, it's gonna take the RF input within this range, and it's gonna mix with the first local oscillators whose frequencies are controlled by the microcontrollers in order to produce a first IF having a fixed frequency of to about 2.4 GHz. And then this IF is gonna pass through a bandpass filter to reject any unwanted noise and images. In the second stage, very similarly, the IF, the first IF from this stage is again mixed with a second local oscillator whose frequency are fixed at about 2.45 GHz, so that the second IF produced has a frequencies of about 45 MHz. So as you can see, like the frequency is down converted to about 245 MHz. And this second IF is then fed through a bandpass filter and then amplified by a log detector and goes through an A to D converter, so that this digital output from this A to D converter is recorded by the microcontroller. Our biggest constraint on this filter, in this project, is the final bandpass filter, because it has a very narrow bandwidth. Therefore, any signal, any frequencies falling outside of this range will be severely attenuated. Next one, software and firmware. So first of all, I want to talk about the microcontrollers. We decided to use the Teensy 3.2 as our main microcontrollers. So the purpose of this Teensy is to switch the first array of frequencies, as I mentioned before, like between 2.4 and 4.4 gigahertz, so that in order to measure the frequency components existing in this RF input. So technically, while sweeping this array of frequencies, the Teensy is going to record any specific frequencies on this array at which the second IF produced has a frequency of 45 megahertz, and then the Teensy is going to back calculate the frequencies existing in this input signal. The second purpose of the Teensy is to set the second array to a fixed frequency of about 2.45 gigahertz, and then it's going to reach the digital output from the A to D converter. The reason we chose the Teensy 3.2 because it's compatible with the Arduino IDE, so that it's very easy to program. It's also much smaller and more compact compared to all the microcontrollers like Arduino Uno, Raspberry Pi. Also, last but not least, the Teensy has a 3.3 volt logic high. This is very important because the local oscillator only takes a 3.3 volt, but not 5 volt as usual. On the software side, we use a LabVIEW to design a GUI. So this GUI is a main user interface to communicate with Teensy, recording the data from the Teensy, and then it's going to display the spectrum for visualizations. So basically, the GUI is like the screen of the spectrum analyzer. Regarding our test plan, in order to test our project, we need the following lab equipment. First of all, the signal generator to generate a desired frequency signal, a spectrum analyzer, oscilloscope, and network analyzer in order to analyze the spectrums. The test procedure including, first of all, test individual components, like we're going to test the log detectors, the bandpass filter, the low-pass filter, to make sure that all of them meet the specification as described in the datasheet. And then we're going to construct a test fixture for branches to ease the testing process. And then we're going to test branches of the super heterodyne receiver. And then we're going to test the firmware on the Teensy to make sure that we can manually control the first array of frequencies. And then we're going to test the GUI, make sure that the GUI communicates well with the Teensy. And then finally, we're going to test the firmware that make sure the Teensy is going to reach the ADC output value properly.
All right, I'm Kevin Mosco, a member of the software team. And here you can see our bill of materials that we've constructed so far. So the bill of materials mainly consist of our analog hardware components and mixed signal components so far, as a lot of the software items that we'll be using have been identified as free. So in our bill of materials, there's really 3 different states of our components. So there's a white state, which indicates that the parts have been identified as needed but not yet ordered. Green are parts that we've identified as needed and we've also ordered and in some cases tested them. And yellow are parts indicated as needed, but also some other components are likely to be also included with that part. So while we feel we have a pretty complete list of what we need and what we've identified as needing, we're pretty certain that other things will arise that we'll need. So we expect some PCB boards to be needed to place some of our filters and in this case our AD converter on. And so we expect our bill of materials to increase a little more by the end of the semester. As you can see, if I move my screen a little bit, the total cost is about $500 for our spectrum analyzer, which is a great improvement over the classroom spectrum analyzers. that are currently on the market, which run about $2,500. And this next slide shows our project timeline. So we first started out our project by just researching and trying to understand the superheterodyne structure and also how a spectrum analyzer operates. Once we felt we had a good understanding, we realized that we could split our team into a software and hardware team to utilize the skills that each one of us had been learning and developing on co-op. So once we had our team split, we began designing individually the software and hardware with good communication with each other. So that really is what the majority of our work this semester has been, is design. We feel we're in a good place now that we can finish and start ordering parts so that they arrive towards the beginning of Christmas break. And then over break, we feel we'll be able to start assembling some of the hardware and also compiling some of the software to put us in a good position to next semester to tie everything together. And then on the second slide for the project timeline, it just includes some more detailed steps and items that we've been completing throughout the semester. So as kind of anticipated, there have been new things that have arisen. For example, we experimented with a software-defined radio to give a sort of benchmark of what our spectrum analyzer should do, even though our spectrum analyzer will have hopefully a lot better performance than the software-defined radio. And then also some things have been delayed. Just designing the hardware components took a little longer than expected, and so there's kind of a chain reaction of delay with some hardware testing and whatnot. But none of these delays are so severe that we feel we won't be able to make this up over Christmas break. While our project has proceeded smoothly so far this semester during the design phase, there are some outstanding issues of concern that we'd like to address and research for next semester. One of these main issues of concern is how we're going to power active components in our circuit, such as the local oscillators, amplifiers, and ADC. These different active components need different voltage levels to power them, and we need to design a power supply circuit that can provide these voltages to these components. Also, we are concerned that the noise from the power supply might negatively affect the performance of our spectrum analyzer, given that we're using such high frequency sensitive components. Also, we have some concerns about how electromagnetic interference will play into our design with the components being so close to each other, and we're hoping that by using a plexiglass enclosure, we might be able to combat some of these reservations. And then lastly, with so many components being cascaded and chained together, we're concerned about impedance matching between the components. And already when we were testing our final IF filter, we found that we were getting poor performance and that an impedance matching circuit was needed. And when the impedance matching circuit was built and added, the filter performed much closer to the desired specifications. In conclusion, because we have so many individual parts that are reliant and connected to each other, there'll need to be a lot of individual testing on these components to ensure that they're working according to their specifications so that we can troubleshoot if a problem arises. Also, with all these parts, it's going to take quite a bit of time to integrate them all together, and a lot of troubleshooting will need to be done, and we expect that to take the majority of next semester. And here you can see references that we use to research how the superheterodyne structure works that helped us come up with the design and the individual specifications for our components. And here is that picture that we saw earlier, which summarizes our design.